Hi guys, today's video we're going to be looking at uniform circular motion again, but now we're going to be looking at the forces involved when we have that circular motion. So from before we remember if we have some object and it's moving around in a circle, so at this point it would have some velocity here. We know that this is basically only going to happen when there is a acceleration, which we call a radial acceleration, pointing towards the center of that circle, and that radial acceleration, furthermore, must have the form v squared over r in order for this ball to keep traveling in uniform circular motion. So this is sort of what we had already learned, and the only thing we're going to do today that's going to change this is we're just going to look at the forces acting. So we want sort of to extend this to a radial force, which will be the force that will keep this object in circular motion. So from Newton's second law, we know that the sum of the forces is ma. So if we want our force to be pointing towards the center, this will basically be saying the sum of the forces should be mass times the radial acceleration, and that will keep it in the circle. So therefore we get our big equation here, which is the sum of the forces should be equal to mv squared over r in order to maintain our uniform circular motion. So this is basically the one equation we'll be looking at in this video today. But there is one big misconception that students have about this a lot, and that is that this radial force itself is not sort of an interaction force that we've been looking at. So it's not a force that's going to act on the object itself. It's going to be the result of other forces. So that's to say we have things like normal forces or tension forces or gravitational forces, and those are all real forces. This is just going to be a way of labeling those forces when they're pointing towards the center of a circle and causing circular motion. So we can see that if we just think about a scenario where we have maybe a bucket and tied to a string, and it's going to be traveling around in a circle here. And so at this point we know that there are only two forces acting on this bucket. There's no radial force itself acting on the bucket, but we do have a tension force and we have a gravitational force. And those are both pulling down. And so we see at this point those are pulling towards the center of the circle. So what we could do to remind ourselves that there is some force pulling towards the center, which is going to cause this circular motion, is just label the sum of those forces as a radial force. So in our free body diagram, we want to draw this separately. We want to draw it off to the side just as a reminder. These two forces have to add up to equal mv squared over r in order to have the required force towards the center to keep this traveling in uniform circular motion. Okay, so let's look at this in a concrete scenario. So the problem statement for today is as follows. A small car with mass 0.8 kilograms travels at a constant speed on the inside of a track that is a vertical circle with radius 5 meters. If the normal force exerted by the track on the car when it is at the top of the track is 6 newtons, what is the normal force on the car when it is at the bottom of the track? At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have the scenario drawn out over here. So we see we have the car at the bottom with some velocity v. It's going to move around, and this here is the top of the motion. So these two are the same car, just at different times. And the velocity, again, remains constant. It's uniform circular motion, so this velocity is still the same at the top. And we're told that the normal force at the top is 6 newtons, and we want to solve for the normal force at the bottom. And the only other thing we're given is the radius here. So we want to first draw out our free body diagrams. So I'm going to start by drawing out the free body diagram for the top. So there the car is going to be right here. We see it's traveling to the left, so I'll just remind ourselves we have a velocity to the left here. So now we want to draw out our forces, and so in this scenario we only have two. And that's going to be f of g and f of normal. So that's to say this car up here is experiencing some gravitational force pulling to the ground, so that's downwards. And then the normal force is again going to be perpendicular to the surface, so that's just going to work to push downwards as well. So we see we have this scenario, and one other thing we want to do now is we want to label, and again remember this is not acting on the car itself, but it's a sort of a reminder. We want to label we have a radial force here because these forces both point towards the center. So they must add up to give us our radial force, and we know the form of that force. So we'll leave that alone for now, and we'll move on to the bottom of the motion. So at the bottom of the motion, we have similar scenario, but a little bit different. So at the bottom here, we have, of course, it's moving to the right with the velocity. So here now we see our gravitational force is still pulling us downwards. So we still have Fg pulling down, but now our normal force is flipped. So at this point in the motion, we actually have a normal force pointing upwards. So again, the normal force is going to push against the surface so that the car does not fall through the bottom. At the top, it's sort of pushed downwards so the car wouldn't go through the top of the ramp. So here we see we have our two different free body diagrams. So now we see why the normal force will not just be 6 newtons. It's going to have to change because the direction on each of these forces is different. So if we want to look back to our top motion, we know a little bit about the top. We know the normal force. So let's relabel this F normal top. That's what I have over here. And similarly, I will label this F normal bottom to be careful. And so here we see we can do what amounts to Newton's second law for the top of the motion. And that will give us the sum of the forces is just going to be equal to Fg plus Fnt. So in this case, I'm not going to worry. Our coordinate system is sort of implicit here, but we're just going to say the radial force will be our positive direction. So basically, in words, what we're doing is just saying the gravitational force plus the normal force at the top must be equal to our mass times our radial acceleration. So again, this a radial is the important point here. It's going to be equal to ma, but we know our acceleration must be radial acceleration to keep this traveling in uniform circular motion. So at this point, we can now solve pretty well. We know Fg, we have enough information to solve for that. And we know the normal force at the top is 6 newtons. And so the only thing we want to note now is that this a radial is of the form v squared over r. So given this information, we can now plug everything we know in and solve for our velocity. And so if we do that, we should be able to get a velocity of 9.3 meters per second. So that's to say, since this is uniform circular motion, the car should be traveling at that velocity throughout the whole loop. So now we can actually use that velocity over here. So the one thing that we didn't note quite yet is that there must be some radial force. In this case, pointing upwards. Again, remember the radial force points towards the center of the circle. So this here is the scenario where it's at the bottom. So that must be pointing upwards. So we can similarly do Newton's second law, again taking up to be positive because that's along the direction of the radial force. So for this scenario, we have sum of the forces should be the normal force will be in the positive direction along the radial force. So F normal bottom. And this should now be subtracted off from the gravitational force. So we now have the normal force along the radial direction minus the gravitational force, which is opposite, must be equal to mv squared over r. And that's the same reasoning over here. We want it to be going in uniform circular motion, so this has got to be mv squared over r. And so at this point, we now see why the normal force is going to be different, and we actually see that it must be larger because we see we sort of have to fight against the gravitational force. Whereas here, the gravitational force was helping us out to give us our value of mv squared over r. Here, it's going to sort of be hurting us, right? It's pointing in the wrong direction. We want a net force going up, and we have this pointing down. So we can solve this now directly, plugging in our values, and we should be able to solve straight for the normal force at the bottom, which is actually what we're asked for. And so you can follow along in your solutions, but you should get a normal force of 21.7 newtons. And again, this is pointing upwards towards the center of the circle. So let's review how we got this answer. We first drew our free body diagram for each part of the motion, top and bottom. On this, we noted that the sum of the forces for both of these must point towards the center and have a magnitude of mv squared over r in order to keep the car traveling in uniform circular motion. So then we looked at the sum of the forces for the top motion, and at this point we saw we could solve directly for the velocity that the car was traveling at all times. Then we plugged this velocity into the motion at the bottom and solved directly for the required normal force. Okay, so I hope this video helped you understand a little bit about the role of forces and how you deal with forces in uniform circular motion. So if you have any comments about this video or any videos, please leave them on the link in TED, which should be next to this video link. Otherwise, thanks for watching.